Hello everyone, this is question 2E from the practice exam of Computation to 2023. This question asks us to make a parametrized counter, and it differs quite a lot from what we have done so far. So there's no finite state machine diagram, and it might not be that straightforward to implement it. So we'll kind of I'll try to kind of show you how you can approach these questions when you have them on an exam. Well, the first thing is really try to understand what it is that this machine that you're going to kind of build really does. So the parameterized counter in the sense. So so you have a clock, you have a reset, you have a TR, which in this case they explain what the TR will do. You have a CF, you have some t-value parameters, you have some multiplier, and all that. Let's firstly really try to understand what is happening. In this assignment, you create a variable counter, parameterized counter, and the counter is triggered. So when the counter is triggered, it will run for a number of cycles, and then stop counting until it is triggered again. So as you can see here, so when you have TR, when TR gets 1, and you have also some multiplier, CF, well, so we can already kind of tell that when the device is counting, so it basically will act like a sort of, basically like a timer. And while it is counting, it will keep CF low, and when it stops counting at some point, CF is asserted back to high. And and then they say, okay, trigger, the counter. If the counter was, one thing they specify is that if the counter was already running, nothing should happen. So the red part here, what that denotes is that it basically means like a sort of don't care. We don't care whatever happens with the TR. While I'm running, while I've been triggered, I don't want to care anymore what happens with the TR. I just have to complete for the amount of clock cycles that I have to go through. So kind of count that. And then you have CF, which indicates the counter that the counter is running. Yeah, basically this is the signal which is going to say, okay, my counter is now kind of running. And then you have t-value, but this one is not an input or output, it's a parameter. So it's like a constant thing. Yeah, so it says, okay, value of n. For example, when the multiplier is 1, CF should be low for t-value of 1 cycles. Your module must support t-values of at least 32 cycles. Okay, so but what this means is that our kind of registers which we'll have to create should at least support 32 as a decimal. Okay. Now we have multiplier, and we have also this other input which is called the multiplier, and this is basically based on the input which is given specified here. We want to basically kind of multiply the t-value and count that many times. Now, to make this a bit clearer, I'm going to even spend a bit more time. So you have, imagine if you kind of have like this finite state machine, like this very basic, right? So we are not actually going to approach this problem really as a finite state machine, but you can kind of think of it as that, because when you're at this kind of like the idle state, so you start at the idle state and you wait until the trigger is asserted high, so here, and when the trigger is asserted high, you want to jump to kind of this next state, but we are not really going to like say, okay, this is current state and there's a next state and all that. We're going to code it more directly in Verilog. So okay, and then when the counting is complete, you want to go back here and then check if there's a new TR and all that. And you also want to kind of screenshot the multiplier and multiply that many times. Okay. So if I kind of try to build this one, you'll have a sequential logic, and you will have the combinatorial part, right? So I'm going to call this sequential, and this is the combinatorial part. Okay, so okay. and kind of always how we kind of combine this two with like the next registers and the registers, and and we want the output to go from here. Yeah, because one thing we can also kind of see is that all the output should always be synchronous, right? So we want to have a sequential logic and not just to kind of randomly assert high or low. So we want to kind of have to keep this sort of synchronism. Now this assignment is quite similar to the lab 1 uh, of the Computation 2 course. So if you have fully understood that, that means that, yeah, you'll not have that much trouble, I believe. But okay, let's kind of start with firstly the first thing they want to say is replace the dot 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 with a reasonable default value. Since they used here t value of 7, I will just go for a t value of 7. Okay. And now let's kind of try to approach the problems. Now we want to have a register where we store how many clock cycles have passed, right? So that is the first thing. So we want to store how many clock cycles have passed. And for the sake of it, I'll make this a 32-bit register, even though it's definitely not needed, but just for the sake of it, it does not matter. And I'll call this ticks. And of course, will have its the asynchronous part ticks next. Okay, so this is for the sequential. Okay. Now I want to, of course, have them kind of sort of the effect register to kind of keep track of the multiplier, and we want to have multiplier as a register. So you want to save it basically, since at this point then it might change, but you still don't want anything to change. Right, so if you do this, then you also want to do this to prevent a latch. You want to do this one. So you have also the combinatorial part of it, like as usual business how we do it. Okay, and now to kind of keep states. Now if we go back to kind of keep states between this one. So if I call this is state 1 and this is state 0, or like the other way around, we want to kind of keep track of the states, right? So we kind of need this register. If I want to call it, I don't know, like counting maybe. Yeah, that should work. So when counting is 1, that means the device is counting. So CF should be 0. And when counting is 0, that means we are not counting. So we are at this state. So at this state, then we want to kind of have the CF equal to 1. Okay, and of course I also need here the combinatorial counterpart. Next. Okay, so we have kind of set it up, this registers, which we'll kind of use. Now let's start with the positive edge clock. Now this is going to be very similar to what we have done in Verilog. In the finite state machine ones, because you will say if reset begin and else begin and you will say here counting 0, just reset all the register you have. Okay, counting 0, ticks 0, and multiplier like 0, and now here just gonna copy this. And like here we're gonna go with next, multiplier like next, ticks next, counting next. Okay, and really this is all for your sequential part, because you want to just like make sure that these things update on the positive edge clock cycles, and we usually gonna do it like business as usual. And you're kind of used to this one from the whenever we did a finite state machine. And now we will create, and now this is where it gets a bit more complicated when we actually want to create the logic behind this. behind this. Sorry, this is kind of disconnected. For the logic behind this counter, so it will get a bit more complicated here. We start with preventing the latches. So we say counting next is equal to counting. So this is also coming. You should be used to this one. Ticks next equals ticks. Okay. Okay. Now we want. So we have set it up these variables. I mean these registers, and this will prevent latches. So I'll just comment here. Prevention of latches. Yeah. Now we go and we say if. So if we are counting, right? So if counting is 1, begin and else begin. So this would be kind of our, okay, here we are at state 0, and here we are at state 1, or the other way around, however you want to kind of call this. And this can kind of loop back to what we drew here. But it doesn't really matter how we do it. You can also do this with a case. So case counting and begin, but I'll just use if for now. Okay, so what do we want to do when we are at the idle state and we wait for the TR? Okay, we want to okay, so now we say if TR, so when there is a trigger, begin, and we say, well, let's set the counting next because I want to already start counting, right? So there has been a trigger here, and then I say, okay, I say that my counting next, so when the next clock cycle starts, I should already be start counting. Okay, so I say my counting next should be 1. Okay. Oh, by the way, here we want to set ticks to yeah, okay, no, that's fine. And then I say here, okay, my ticks should be 1. Oh, sorry, the ticks next should be 1. And then I will have to now also kind of screenshot the multiplier reg. And to do that one, what I'll do, as we agreed that, okay, so it says here that 0, 0 is 1 times, 0, 1 is 2 times, 10 is 4 times, 11 is 8 times. I mean, 1, 1 is 8 times. So I'll just say case multiplier as input, and then AND case. And then here we have 2b00 begin AND. Or we can just do it like this. Say multiplier register next. Oh, by the way, sorry, this one should not be 1 bit, but this should be at least 2 bits. So let me just make sure this is 2 bits because these are all 2 bits. Oh, but in any case, if you want only to kind of screenshot these values, then we would need more than 2 bits, because if we want to store a value of 8, right? Because yeah, like the way to approach this one is that the moment you get the trigger and you kind of keep the multiplier, you decode what this means. So if this means 4, then I want at my multiplier register to have a value of 8, so then I can just like multiply it later. Okay, so I'll actually increase the bit size, so I'll just make it something like I guess 4 bits, just to be sure. It's better to have more bits than have insufficient bits. So okay, I say this, and I say multiplier register next. So if I have 0, 0, then it should be 1 for D1. 51 2b01 multiplier reg should be 42 2b10 should be 44, and then 2b11 48. Okay, so we have set it up the part where we kind of trigger and we jump from this state to the other state. So the next state here would be the counting next. You can kind of think that as that. Okay. Now when we are at the counting stage, what the first thing that you want to do is you want to increment ticks, right? So this is like the part which you this is like the part that you keep track of how many clock cycles have passed. So you say ticks next. Ticks next is equal to ticks. So the number of actual ticks plus 32 d1. So I'll always be incrementing one from my actual ticks value. And this one, yeah, this is clear. If I want to draw this one to just give you a little bit of idea, if I have two registers, right, and this is called ticks, and say it has a value of 4 inside, and then I'm taking this ticks, I am doing some operation where so this is like the combinatorial part, and I add here and I do the ticks plus 1, I will have 5, so the value of 5 here, right, already be waiting. So this is what I can do here. So you'll already be having like the value of 5 waiting at ticks next, but this will only update once your clock signal has reached the high, right? So only when the clock signal rises, thus this register will take whatever value is at its input, change it, and then again, then here would be 5, this would add plus 1, here you would have 6, and that's kind of how the incrementing goes. If you have download 1, then this should not be something very new to you. Okay. Ticks next, ticks plus 1. Okay, now we can continue with saying, if ticks, so now what happens is, if I've reached the number that I want, which I'll just say it's going to be my t value times whatever I store at my multiplier register, begin, end. I say that I'm not going to count anymore, so I say my counting next should be 0, and I also want to reset my ticks next to 32 stay at home. Okay, so this is kind of how we can approach this problem, and and now I can try to compile this one. Oh, this is, by the way, giving a warning saying we're not connected CF. Send CF equal to, and we want to say that, okay, CF, if counting is 1, so counting, we say that, okay, so when we are counting, we want the CF to be asserted to low, and when we're not counting, it should be 1. Okay, now we can save, send CF equal to that, and run it. Okay, and what we can see is that we have not passed all the test cases. Okay, so now we can go and try to debug where the problem might be. If I put my CF DUT and my CF reference, and if I put the clock, what I can see is that, okay, I don't think this part is a problem, but what I can see is that, okay, once I start to count, so I'll just put also the trigger signal. So the moment that I start to, so it gets triggered, and then at the new clock cycle, my CF goes down, I count. One thing that I can see here is that I'm 1 clock cycle late, and this is because we say when we click the start, we should also kind of count, okay, we have clicked the start, then start from 2 basically, not from 1, because you should count also the clock cycle where you kind of started at. So we say this should start at 2. Okay, now we can compile. Okay. It seems to give us a problem. Takes next 31D2. Okay. Oh, yeah, because this should be 32 bits. Sorry. Okay, let's run it. Okay, and now we can see we have passed all the test cases. Okay, thanks for watching.